Okay, so this is Math 146, Section 7.2. In this section, we're going to be talking about geometric sequences and geometric series. The most simple definition or way to differentiate between the two of these is that a sequence, as we've talked about already in 7.1, is just a list. So a sequence is a list. Now, it is a list written in some kind of a definitive order, usually some kind of mathematical um, um, way of thinking about it, so that it's got some kind of a pattern associated with it. But it's going to be a list written in some order. And then a series is when you take that list and you add it all up. So we're going to take the sequence of the terms and we're going to add or sum them all up. That's the most general way to differentiate between what a sequence and a series is. This topic is going to be hit much more in depth when you get to what would be towards the end of Calculus 2. Geometric series and sequences play a very big role, again, towards the end of Calc 2. I'm not going to go too far into depth of that, but it will. So we're going to touch on some of the basics, but I'm also going to do a little bit of proving why things are what they are in more of an intuitive manner, because we haven't really talked about the concept of a limit, which again is something which is hit harder in calculus, and you'll get much more into depth of that. But it's kind of interesting. So if you get the intuition here behind this, then it's pretty cool. But let's jump into how we define a geometric sequence, something which is geometric in its form. And the easiest way to think about a geometric sequence is that you're going to take some kind of a number that you can multiply by every term and get to the next term. What do I mean by that? Well, let's start off with a very simple geometric sequence that looks like this. 1, 2, 4, 8, 16, 32, and so on. What you should hopefully be able to see is, in order for me to get from 1 to 2 by multiplying a number, I would have to multiply 1 by 2. And then for me to get from 2 to 4, multiply it by 2. For to get from 4 to 8, multiply it by 2. 8 to 16, multiply it by 2. So I'm multiplying by the same number every single time to get to the next term. The number that we are multiplying by is what is called the ratio, the common ratio. So in this case, the common ratio, which we call lowercase r, is 2. And again, it's because 1 times 2 is 2, 2 times 2 is 4, 4 times 2 is 8, and so on. So if you were just given a list of terms, and this one I think was relatively obvious, but if you were just given a list of terms and you're told that the sequence is geometric, you can always find the common ratio by taking any two of the consecutive terms, for example, 16 and 8. Taking the 16 and dividing it by the previous one, 8, will give you 2. Likewise, if you were to do were to have done 32 and 16, 32 divided by 16 is 2. That would be your common ratio. So in order for us to determine whether a sequence is geometric, that's what you're looking for. Do I have exactly the same ratio being multiplied every single time to get to the next number? So we can just do one more quick one. Again, this is a relatively easy one. These are not extremely challenging. We have 2, 6, 18, 54, 162, and so on. And if you're looking at that and you're thinking, oh, I'm not really sure, well, again, take any two consecutive terms and test it. So let's take 6 and 2. If we take 6 and divide it by 2, we would get 3. Take the next two set of consecutive terms, 6 and 18. So 18 divided by 6. And again, it's always the furthest term or the term of the greatest a sub value, I guess you would say. Like that would be a sub 3 divided by a sub 2. You would divide it. And then if you take 54 and 18, it would also give you 3, and that works for every term in the sequence. So that tells you that your common ratio, R, is 3. All right, I think that's a pretty basic understanding of how a geometric sequence works. Now, the common ratio can be just about any number, with a small exception. In order for something to be geometric, your R value, your common ratio cannot be 1, because if it's 1, it does not follow a geometric pattern, or basically what will end up being an exponential function or an exponential pattern. So your base, your common ratio that you're multiplying by cannot be 1, because if you multiply a number by 1, it's just going to give you the same number every single time. So that doesn't actually work out. And it also cannot be 0, because multiplying any number by 0 is going to give you 0, and every resulting number then would be 0, so that also doesn't work out. Every other number is perfectly fine to be a geometric, unless I'm missing something, but I don't think so. All right, so we want to determine whether a sequence is geometric. This time we're going to be given the form, meaning we're going to be given that we've got some kind of an S sub n, and it's going to be 2 to the negative n power. So if we want to determine whether the sequence is geometric, we could certainly just start writing out a bunch of the terms, and there's no problem with that. Excuse me. And we could take any two of those consecutive terms, divide it, and then take two different consecutive terms, divide it. And assuming that this is geometric, they would all be the same. Or what we could do is just say, well, in general, whatever term I pick would be my nth term. So for example, in the one that we did above, if I wanted that one right there to be my nth term, and I want to divide it by the previous term, this one right here, that would technically be my n minus 1 term. It doesn't really matter which term we pick to be our nth term and which one we pick to be our n minus 1 term, as long as they are consecutive. So what we can do instead to figure out whether this is geometric and whether it's got a common ratio is to simply say, I have the nth term. They've given that to me. They gave me 2 to the negative n. That is the nth term. The n minus 1 term, however, we could write out. So we're going to say that the nth term is 2 to the negative n. The n minus 1 term would be 2 to the negative, and then we're simply going to replace n with n minus 1. That would be the term right before it. Of course, distributing that negative up on top there, we would get negative n plus 1. And according to this, if I take the current term and divide it by the previous term, we should get the common ratio. So if this thing has a common ratio, it would be 2 to the negative n divided by 2 to the negative n plus 1. So what I now have is I have a division with common bases, and when you divide things with common bases, you subtract the exponents. So really what I'm looking at is a negative n minus a negative n plus 1. If I distribute the minus sign through there, we're going to get negative n plus n minus 1. Well, negative n plus n goes away, so you end up with negative 1. So ultimately what we have here is 2 to the negative 1 power, which is the same thing as 1/2. So your common ratio in this particular case would be 1/2. I didn't really have to go through all of that procedure to figure this out. If I realized that a negative exponent really just would have made this 1 over 2 to the n power. And because 1 can be raised to any number, and it's still going to be 1, technically I could have written that as 1/2 to the n power like that. In which case it would be very easy for me to see that that 1/2 is the thing which is being raised to the n power, and that ultimately is what you're looking for the geometric. So in its most basic form, again, what you're looking for is some kind of a constant being raised to some sort of n power. It doesn't have to be positive n, it could be n plus 1, it could be a negative n, but you're looking for a constant being raised to the n power of some sort. If that is the case, that takes on a geometric form because it's exponential. Again, 1 and 0 do not work as bases, but anything else will work just fine. So let's just do a real quick example that if I had this as my sequence, so we're going to call this some kind of a t sub n, and my sequence is 3 times 4 to the n power. What we're looking for here is whether this is a geometric, and it's very clearly a geometric because I have a constant number being raised to the n power. The 3 that's out in the front there is not being raised to the n power. Technically, that is 3 to the first times 4 to the n, but the 4 is being raised to the n power. So my r value is 4. So this is a geometric sequence. And that's the easiest way to figure it out. You're just looking for that number which is being raised to the n or some form of n power. Now there is a way to derive this next part, but basically this is your general form of a geometric sequence. It's that a sub n, which is your general nth term, is going to be a sub 1 times r to the n minus 1 power. And a sub 1, as we know, represents the first term of the sequence. R represents the common ratio. And again, R can't be 0 or 1 in this case. So let's see if we can actually take this information, this general form, and actually write a geometric sequence in its general form from a list of terms. So we're going to take the list that starts with 10, then 9, then 81 tenths, then 729 over 100, and so on. So we are told in this case that this is a geometric sequence. Again, if you weren't sure, you take the two consecutive terms and you divide them and you would find your common ratio. We're going to need to do that anyway, because if we want to find the nth term of the geometric sequence, we need r and we need a sub 1. Those are the two things that we need. So finding a sub 1 should be the easiest thing if you're given a list because it's literally the first term. So we know that a sub 1 in this case is 10. It's the first term that was given to us in the sequence. We're going to need r. R should be any two consecutive terms divided by each other. Well, given those messy fractions, I think I just want to take the first two terms. We'll take 9 and divide it by 10. So r, so r in this case is 9 tenths. So now we have everything that we need to write our general term. And the general term is a sub n equals the first term, 10, times, should be a times, the common ratio, which is 9 tenths raised to the n minus 1 power. Okay, and that is the general or nth term of the geometric sequence. And why is that important? Because now I could find any term of the geometric sequence that I really wanted to. If I want to find the 9th term Maybe that's what they're asking me for. So we want to find a sub 9. Well, that would be simply plugging in or substituting 9 in for n. So it would be 10 times 9/10. Plugging in a 9, you would get to the 8th power. I don't know what that is. I'm not really worried about working it out, but that's what your 9th term would be. So that's basically what you would do in order to find any specific term of that sequence. Now let's say we want to actually start doing more of something which is a series, and we want to add up or take the sum of these terms of the geometric sequence. Okay, so I could just give you the formula and say, here it is, use this formula. But I prefer to actually kind of show where it comes from. I think this is kind of a cool thing. So let's start off with the fact that we know that the sum of the first n terms of the sequence is basically just going to say, okay, I'm going to start off with the first term. My second term is what I get after I multiply the first term by r. My next term is what I get after I multiply the previous term by r, which will give me a times another r, which would be an r squared. Make that actually look like a squared. There we go. And that's going to happen all the way up until we get to the n minus 1 term. All right. So if that would be the sum of all of the terms up to the nth term, because that's the formula that we have. Let's take and multiply each side of this equation by r. So now I'm going to multiply the left side by r, and I'm going to multiply the right side by r, which is basically just going to give me an r times every one of my other terms. So I have a sub 1 times r plus a sub 1 times r, technically times another r, plus a sub 1 r squared, again, times another r, plus all the way up till we get to a sub 1 times r to the n minus 1 times another r. I'm going to simplify the second line just a little bit. So that's still going to be r s sub n. This one is going to be a sub 1r. This one is going to be a sub 1 r squared, a sub 1 r cubed, all the way up till we get to a sub 1, and then r to the n minus 1 times r, adding the fact that that's r to the 1 technically at the end there, you're just going to be left with r to the n. Again, multiplying the common bases, you add the exponents, which would be n minus 1 plus 1, so you just get n. So now what I'm going to have is I'm going to deal with the fact that I've got this one and this one, which have a bunch of common terms. And ultimately, again, what I'm trying to find is some kind of a sum of the first n terms. That's ultimately what I'm trying to find. And I'm trying to find it in some kind of a usable fashion. So what we're going to do is we're going to take the top line and we're going to subtract the third line. So ultimately, let's see, let's use a different color for this. What we would get is s sub n minus r times s sub n. That's subtracting that and that. But of course, I got to subtract this stuff on the right-hand side. I've got this a sub 1 term on the top right here that I have no other constant terms without r, so it's just going to stay a sub 1. But then what you should see is that this term, a sub 1r, is going to get rid of that a sub 1r when we subtract. A sub 1r squared is going to get rid of that a sub 1r squared when we subtract. And this is going to keep happening all the way up until we get to this term out here. So this one's going to go away. I didn't write enough terms on the top line, but that's going to go away. The a sub 1 r to the n minus 1 is going to get rid of what would technically have been right here before this one. So all that I'm going to be left with on the right-hand side is this. But it's going to be subtracted because I don't have any r to the n terms to subtract it from. So on the bottom here, we're going to have a minus a sub 1 r to the n. And again, what we're solving for is an s sub n. We're solving for the sum of the first n terms. So I've kind of already got them on the correct side. I've got them on the left-hand side. I'm going to factor out an s sub n, which is then going to leave a 1 minus r. The right side hasn't changed. And then to solve for s sub n, we're simply going to divide both sides by 1 minus r. And that's going to be a very nice, usable way to find the sum of the first n terms. For example, if I wanted to find the sum of a sequence of, I don't know, 12 terms, 12 would be my n value. I should be able to figure out my a sub 1 value and my r value because I will already have some information about the sequence. So all I would really need is a sub 1 and r. Plug all that stuff into the right side and you have your sum. And we're going to go ahead and use that idea to find the sum of a relatively basic sequence. The sequence that we're going to be given is 1/2 to the n power. And we want to find the sum of the first n terms of that sequence. So if you were to start writing the terms out, which we won't always do this, but if you were, it would be 1/2, since 1/2 is the first term, because if you plug in 1 for n, you would get 1/2. The next term, well, I'd have to multiply a half by itself in order to get the next term, which would be a 4th. Multiplying by another half would give you an 8th, then a 16th, and that would keep happening all the way up until we get to the nth term, which of course is 1/2 to the n, because they've given that to us. And we want to find an expression for the sum, oops, n equals, sorry, it should be k equals 1 to n of 1/2 to the k power. Okay, that's what we're trying to find. So what do we know? According to our sum formula right above, we know that s sub n is going to be the first term, a sub 1, which is 1/2, minus 1/2 r to the n power. Okay, so that's going to be r raised to the n power, divided by 1 minus r. And I completely forgot that r is 1/2. Hold on. Let's plug that in. 1/2 to the n power. There we go. That looks right. And not that you need to do this part, but I can take the 1/2 from here and from here out to the front, which would leave you with a 1 minus 1/2 to the n over 1 over, sorry, excuse me, over 1 minus 1/2. Of course, the 1 minus 1/2 in the denominator is a half. So we're going to erase that and just write 1/2. And then what you have is the half and the half are here are going to cancel out. So ultimately, I have 1 minus 1/2 to the n. And that right there would represent the sum of 1/2 to the n power, or in this case, the sum of 1/2 to the k power because we changed the letter. But that would be an expression that you could find the sum now given any n value that we wanted to. If I wanted to find the first 10 terms, I would simply plug in 10 for n, and I would have the sum. So that would be a nice expression there. And just for total clairvoyance, there is a way to actually perform these sums on your calculator, on your TI-84 type calculator. To me personally, it kind of defeats the purpose of us understanding how all this stuff is done in the first place. it does make the process quicker and easier, but you really do kind of need to understand how and why all this works. So I would much prefer not to use the calculator in order to find these sums. Um, but again, you'd have to have an actual n value to be able to find the sum on the calculator. So I'm not really going to go through that right now. All right, that's going to finish up video one. We're going to come back with a second video, and in the second video, we're going to actually talk about what is called an infinite geometric series. So basically the idea of adding up something which has an infinite number of terms instead of an n number of terms.